like I shared some performance numbers, and it was something like, the I had a job. The total time it took to run that job was 33 seconds. This was the script to recreate the past states of the program.
Uh-huh.
Um, and then I think we determined that about 80% of that, well, about 20%, I'll do it, 20% was spent in doing database stuff.
Okay.
And then there's about 80% that's, I'll just call it
Okay.
other stuff, which includes parsing and other processing. But essentially, it's mostly Python doing its work,
Mhm.
with just the statements, loops, and data structure stuff. Um, so the plan was I'm gonna rewrite this whole thing in C, and I already found that if I rewrote just the parsing part in C, I could get like a 30 times 30 time speed increase.
Mhm.
So my thought was, well, if just the parsing I can get a 30x increase, I can probably expect all of this stuff to get a 30 times increase,
Uh-huh.
which will probably shrink it very substantially. We'll probably shrink it down to about here, right?
Okay, yeah.
And then after this 30, like I'm gonna this 80% is gonna be 1/30th the size of what it used to be, which
Yeah.
is gonna be like this tiny slice here. So we're gonna end up with this. I sort of expect the database part won't be improved because the database part is actually calling into the SQLite driver, which
Mhm.
itself is implemented in C in a low level way.
Mhm.
So I don't really expect that to improve. So I expect the end result to be this portion here. And when I did the calculations, if I calculate it that way, I would end up getting like close total wise out of this 33 seconds, I would be down to like 8 seconds, which is about 5 times better
Okay.
overall.
Mhm.
Um, and so I rewrote the thing in C. It took a lot of learning on my part. There's a lot of things about C that I learned. So yeah, basically we were here. My prediction was I'm gonna get to about 5 times faster than the previous version, than the Python version. And after I did enough work with the C version to be able to do a direct comparison, it was more or less right there, about slightly faster than 5 times actually.
Okay.
And then um, oh, I'll show you some numbers. Are we? Perf. Oh, okay. I had a few. Oh, okay. I'll talk about that one later. Okay, this was it. So I ran this. I did a calculate the Fibonacci number for the 25th Fibonacci number.
Mhm.
It was a simple program that just had a lot of execution in it.
Okay.
So on Linux, I was down to 4.6 seconds. With the old Python version, it took 48 seconds. The newer Python version, it took 44 seconds. So it's roughly 10 times improvement. Oh, initially it was 5 times improvement, and then I found that the database was taking most of the time after that.
Mhm.
And then I actually optimized the database part a little bit by using various SQLite tuning parameters. Just tweaking things here and there to try to get it to go faster.
Okay.
And at the end, what I ended up with is just to have all of the insert statements go in the same transaction.
Oh, okay.
That ended up being the fastest,
Mhm.
and with fewest configuration changes. So it's just that way right now. So the loop that so here it just says begin transaction, and then this while loop does all the event processing one after another, line by line, and then just end transaction. And that ended up being the most performant.
Oh.
I played with a bunch of these other settings, which I
Mhm.
found online that you can do these things, and some of them did give me a benefit, but at the end it was like, this is all I needed. So
Okay.
these are commented out right now.
Okay.
But yeah, so basically after that kind of performance tuning for the SQLite, I was able to get 10 times improvement. I did a test on Linux, and I did a test on Mac.
Nice.
This is on Mac. The Mac was actually more dramatic. I was down to 3.8 seconds, and the Python took a whole minute to do.
Oh, wow.
Yep.
Very cool.
Yeah. What else did I want to say? Oh, one one thing that I learned, I don't know, maybe we should wait until next time because we're kind of getting the end of our time. I found this statistical sampling way of doing profiling, which you didn't really need a profiler to do. You can just kind of manually do.
Okay.
And that's how I found that uh, that's how I determined that the database was taking the most of the time. Like after this sampling method, I found that 70% of the this is random probabilistic, but I did 20 trials and 14 of them was in the database transaction phase. So it's in the database. And then a couple of other ones are still in the SQLite driver, even though it wasn't the transaction phase. This is before I did the performance tweaking. And then after the performance tweaking, I did the same thing. After the performance tweaking, I did the same thing, and I did 20 samples. And then most of them were doing, even though we don't no longer have database transaction stuff inside the samples, because I only have one transaction and the transaction is finished at the very end. But I still had a lot of things going on in the database. I mean, in the SQLite driver. So this is all SQLite driver stuff. So that's how I was able to determine that most of the time is being spent in the database still. So
how did you create this report?
how do I create this report? Okay. So I actually went Googling C profilers and recommendations for, I found this Stack Overflow question called recommendations for C profilers. And then some of them gave me the recommendations. One is called gproof. The other one is callgrind and kcachegrind, which is part of Valgrind, which I've been using for finding memory leaks and memory usage problems, which is extremely good for that. So I did try both of them, but I didn't have a good luck with either one. just because of different reasons. Like the gproof gave me some very weird numbers, so I didn't trust it. And maybe I'm not using it right, or it's has a bug on my system or whatever. And then this call grind thing, it required a GUI that only works on Linux. And I have a Linux computer, but I don't have a GUI for my Linux computer because it's in the cloud. But then I read this guy's answer, and this is so funny because this guy is like, you don't need a profiler. Here's what you do. And then like he's basically like extremely enthusiastic about his methodology for performance profiling. And he explains the whole thing in a series of Stack Overflow answers. Like historically, he has written so many of these that he just links to them now. And so this is like a summary post. And so I just read through his stuff, read through a few of his Stack Overflow answers. And he even, in one case, he made a video showing how you would do it. So basically, this is what you do. You run the job. It has to be a job that's kind of long running. And the way I made that is I just gave it so much data that it necessarily has to be long running, right?
Yeah.
So, so if I do this, for example, I run it on this log, it'll be a very long running process. And then what I do is run it inside the debugger. Run it inside the debugger, and then I'm gonna use the R command to get it to run. And now it's running. And then while it's running, I'm gonna just interrupt it by hitting Control-C.
Okay.
And now I just stopped the program at whatever point in time it was at while I press Control-C. And at this point, I'm actually paused inside the program, and I can do a stack trace by using the BT command, which stands for backtrace. And now I have the stack trace of the program at wherever I stopped it.
Okay.
And so you just, so this is a sample. So this is a sample now. And the theory is if the slower parts of the program are more likely for me to stop inside of, right?
What? Okay, I got it. Okay, I see.
Does that make sense? Like if there's a fast part of the program, it's very unlikely that if I just randomly stop you, it's going to be in the very fast part because that just went by really fast. But if it's the program is spending a lot of time in its slow parts, I stop it. It just has a higher probability of stopping at the lower part, the slow parts. The slower the part is, the higher probability I'm gonna stop in the inside there.
That
right?
makes sense. Okay.
So that's the theory. So I just do this like several times. I did it 20 times.
Okay.
And then I ended up with this report. So sample one, I was there. You can see the entire stack trace, which is really nice because like a lot of this I wrote, right? This is mostly my code until we get into the SQLite driver. That's not my code anymore, but I can sort of, I can, you know, I can understand the context basically. So I had 20 of these samples and I looked through each and I just categorized them in the way that makes sense for me. So I summarized them further here. So here, like 5 of the 20 times I landed on this exact same line.
Okay.
1 of the 20 times I landed on this line. And then 6 out of 20, I landed on this line. So you can get an overview of what happened. And obviously the ones where it kept land on that same line several times, well, yeah, that's probably a bottleneck or something, or it's just happening a lot in the program. But at a higher level view though, I further categorize this to like if you look at this line of code, that's inside the SQLite driver. That's inside the SQLite driver. That's inside the SQLite driver. I determined that 80% of my samples, the code was spending time inside the SQLite driver.
Mm-hmm.
And 3 times out of 20, it was not inside of the SQLite driver. 2
Okay.
times out of 20, it was inside the UT hash library, which is the hash table library that I'm using.
Okay.
C does not have built-in hash tables, so I had to grab a library
Okay.
so that I have hash tables. So there's 10% that the hash table might be responsible for, but the 85% is more or less is the database driver is responsible for.
Okay.
And obviously this is not super accurate because it's a random statistically based thing. I only took 20 samples, but obviously if you did this 100 times, you will get more accurate answers. But I think more or less you can see the big picture from just
Yeah.
that many.
Yeah, exactly. Yeah, I like this method. This is great.
Yeah, I like it too because it's very very basic. You don't need a lot of fancy tooling to do this. You can just do it yourself. And I can see it wouldn't be very hard to automate this process.
Yeah, exactly.
Either.
Mhm.
Yeah. Okay.
All right.